Okay, so remember where we left off, we were talking about oscillating or harmonic oscillators. And so basically it's about something in motion. So harmonic motion is about something in motion that repeats a pattern. Okay? And so let's just jump into it. You don't have to write these down. These are some of the terms we're going to talk about. Oscillation, we talked about that last time. Equilibrium, we talked about that last time. Amplitude, how much it swings back and forth or up and down depending. That's there. Now, dampening is a new one. This is what happens in the real world. If I swing a pendulum, if you swing on a swing, eventually you slow down and stop. If a car is rolling, if you put your car in neutral, it will roll, but eventually it'll stop. Sometimes we can force dampening. That's what brakes are on a car. They're a dampening force. Period is how much time it takes for you to complete that one cycle. Frequency is the inverse. And then phase is something we'll talk about today. With waves, you can have interference patterns. They could be constructive or deconstructive. In other words, if I have, well, we'll dive into that when we get to it, okay? So you don't need to write this down. These are just a list of things we're going to talk about. So you do need to start writing all this stuff down. I might need to turn my face off because I'm not going to do this thing where I'm constantly moving my face around. So many real physical systems oscillate when they are disturbed. So think of a pendulum on Earth. A pendulum just kind of hangs there. If you put a mass on a spring, it'll stretch the spring a little bit. Maybe it depends on how strong the spring is. But it'll just sit there. And then think of, they say vibrating rubber band, but think of a guitar string. If you have a guitar and nobody's plucking the string, it's not going to make a noise because it's not vibrating. It just kind of sits there. So musical instruments do this, geological formations in an earthquake, wind-driven skyscrapers, atoms, and a solid. So those are examples of oscillators, okay? Now, in physics, we start by talking about pendulums and mass on a spring and vibrating strings and stuff like that. But in the real world, musical instruments, one of the things, I don't know if I shared this with your class, but I think 220 is, I don't know, it's one of the lower A. So the frequency of 220 is A. If you double that frequency, remember that frequency is the number of cycles per second, to 440 hertz, that's the next octave higher, right? And then if you double that again, 880, that's A as well. That's the next octave higher. So harmonics itself is based on the waves or frequency. Geological formations, when an earthquake rumbles and it causes vibrations, those aftershocks are actually forms of harmonic motion. Skyscrapers, if you go to Chicago, Willis Tower sways a couple of feet in both directions, in all directions. So the skyscrapers in Chicago, and we're very fortunate to be that close to Chicago. It's really kind of cool and neat. I remember I went to Austin not too long ago, and the Uber driver that was driving us to our hotel from the airport said, we think we saw Austin from the airplane. And the guy said, oh, all the skyscrapers, they had like 3 buildings. I was like, oh, okay, guy. But God bless them. I hope they do well. I hope they grow. But, you know, Chicago, there's so many skyscrapers, and some of them are just apartment buildings. But those buildings have to be designed to sway. In fact, there's a famous scientist that made a machine that was called a resonance machine. And he said he could make a building in New York fall to the ground if he tuned into the frequency of the building. In other words, if he figured out how to tune into the building, he would increase. And it's kind of similar to what we did with the tuning forks. Remember, I had the tuning fork, and then I had the tube that was tuned to the same frequency. When you put them together, it was twice as loud. Well, I could do it real quick. I might have to turn my camera back on. Let me make sure I get the right one. Okay. So I'll turn my, well, I can't turn my camera back on, can I? Let me see. Oh, well. Anyways, here, this is tuned to 880 hertz. This is tuned to 880 hertz. There's the tuning fork. Watch what happens. So basically what's going on there is they're tuned into the same frequency. The vibration of one causes the other one to vibrate, and it gets, you double the vibration. That's constructive interference, sort of. So anyways, that famous physicist, you guys know what his name is? Tesla. Nikola Tesla. That's what the cars are named after. He did a lot of work with electricity, but he also was really into harmonics and resonance and all that stuff. All right, let's move on. Does everybody have this copy? All righty. Let's continue. So most oscillators have a resting state or an equilibrium position. So when you think of something attached to a spring, it's the free length. It means if you don't touch it, if you don't apply any force to it, if you just leave it alone, that's where it will rest. That's what we call the equilibrium position. Now, what we move it away from that equilibrium position is called the amplitude. Okay? Now, for oscillators, it's going to go away from it, and then it's going to go on the other side from the equilibrium. So if you think of a pendulum, it'll swing left and right, and it'll go right through the equilibrium position. If you think of something on a spring, it'll go right back and forth, just like the diagram you see here. Make sure you sketch those pictures out. They'll be helpful when you go to do your homework. So the free length of a spring is really the equilibrium position, but the distance that we travel away from it on both sides is amplitude. Okay. Whoops, I'll leave that up there. One thing I kind of glossed over was is that you have a mass that's doing this motion, right? Now, why is it important to recognize that there's a mass? Well, we need the mass for the calculations in most cases. Some cases you don't. Sometimes it cancels out. The mass in many ways can have an impact on the amplitude, right? Think of a wrecking ball. A wrecking ball is really a pendulum. Do you guys know that? So a wrecking ball is a big, heavy, massive steel ball that's attached to a really big crane. And they lift the ball really high on one side, pull up really close to a building, and then they let go of the ball. And the ball falls like a ball on a pendulum. It gets momentum. Now, to be safe, they build it like a pendulum, right? Because you wouldn't want to just start chucking big, huge steel balls at buildings, because what happens? It might go through the building and roll out on the other side. So wrecking balls are really cool in the sense that they can, they're a little safe because they're tethered to the crane. Does everybody have this written down? Nope, not yet. you. Okay, how about now? Yeah. Okay. So draw all this out. Now, a vertical spring, the equilibrium is where the mass hangs at rest. So the spring has a free length. The free length is just the spring not being pulled or pushed, right? But when you put a mass and you're hanging it from the spring, gravity's going to pull it down a little bit. But at some point, it just sits still. In other words, there's a balance where the force of the restoring force of the spring is equal to the weight or the force due to gravity on the mass, right? So remember, the weight of the weight of the object is the mass times the acceleration due to gravity, which is a force. The spring has a force. When those two equal each other, there's no acceleration, so it's a state of equilibrium. It's not going to go up, it's not going to go down. Okay? So the equilibrium is where the mass just kind of hangs at rest. Okay, it doesn't bounce up and down. Now, if you pull that mass down beyond that resting point, the spring it has a restorative force. It will pull it back up. And in that process, and you say, well, I don't understand. You pulled it down. Why wouldn't it just stay down? Well, you're adding work to the system, right? They were balanced. Now they're not. Remember that when you pull that thing, the further away you are from the equilibrium, whether it be from a spring's free length or an equilibrium with a mass attached, that force, that spring force increases, right? Because it's F equals, so let me just write it down. You guys can write it down too. So remember that F equals so the force of a spring is Kx. Oops. I'm going to try to fix that. It looks a little sloppy. Now, sometimes they'll say negative Kx, and sometimes they'll say Kx. If you say negative Kx, it really has to do with the x. It's kind of confusing, to be honest with you. You just need to make sure that you're going positive or negative, that your end result based on where your position in the spring. And remember, this is called Hooke's law. Oops. So if you guys don't remember that from earlier this year, I wrote that down so that you guys would realize that x is the distance that you move away. So as this increases, so does the force. Does that make sense mathematically? Okay. So the further we pull it down, we do work, and it creates energy, right? There's also the spring potential energy. So the spring potential energy, let me write that formula down. Where's my little thing? So when it comes to energy and work, the spring's potential energy formula is very similar. It's potential spring energy, which is, why does it do that sometimes? Kx squared, I think it's 1/2 Kx squared, right? So it's very similar. Right? So when I pull that down, I'm putting potential energy into the system. So that Once I did work to pull it down, it's got to do something because conservation of energy. Okay. All right. Does everybody have this written down? No? So on your homework today, you're going to have to do some problems here. But the amplitude is how far it travels from that position, right? So you could think of it like this. This distance from here to here is your amplitude. So the amplitude is the maximum distance x that is displaced from equilibrium. Okay? So this is our equilibrium point, right? This is our equilibrium point. That's the equilibrium. And so the distance from that point is the amplitude. Consequently, when you let go of that thing, it's going to go up here, which is equidistant. So so this is our equilibrium, so it'll go the same distance in the opposite direction because of the conservation of energy. It should, but we'll learn today about dampening forces. This is a little frustrating, I'm not going to lie. Well, just know that's amplitude. I can't get my pen to write the word amp. Oh, I know what I could do. I could draw a picture or an arrow. So this is the amplitude and this is the amplitude in both directions. A better, cleaner thing to draw would be this is the equilibrium. And we're going to go the same distance. Well, I should have drew the arrows the same length. Let's try this again. And so this is the amplitude in one direction, and this is the amplitude in the other. Okay? So when I put work in the system, it's going to have the spring as the restorative force that pulls it back. Well, it can only go, the energy can only be equal to what I put in the system. Does that make sense? Okay. Do you guys have all this written down? Yeah? I like your hoodie. That's nice. All right, write this down. Hey, it's the same thing I just wrote down on the previous slide. So for a spring, the mass system or pendulum, the amplitude is measured in meters or centimeters sometimes. And when we go to do the physics, in fact, I'm going to cross this out. When we go to do the physics, well, let's do it this way. Let's just say this is preference for motion. Okay. So what that means is if I ask you a real deal, serious physics problem, how fast, anything related to energy, anything that requires us to use a different formula, you're going to need to convert whatever measurement they give you to meters. But if they say how far, what is the, like if it's a simple question that says, what is the amplitude? You can say 2 centimeters. But if you have to do a calculation and you say, what is the velocity of the oscillator at its peak position or something like that, you got to convert it to meters. Anytime you use an equation to make calculations, you got to convert it to meters. So it should be really motion and energy. But if they just ask you about the position, you could just leave it at centimeters, okay? And you could always ask me questions about that. So for types of oscillators, the units in amplitude might be a voltage or pressure. So alternating current operates the same way. Now that's more of a physics 2 concept. In hindsight, I should have offered physics 2 next year if some of you guys were curious about that. Yeah. Yeah, take a pass. Basically it oscillates. Alternating current has a positive charge and a negative charge based on when it rotates around the motor. Unless it's like 3-phase electric or something like that. Same thing with pressure, like sound waves. Fluid waves and fluid pressure. Pressure is basically molecules bouncing off the surface of their container. If you cram more molecules in there, they bounce more. But when they hit the sidewall of the container, when they hit the boundary of the container, they bounce back. So it's kind of a back and forth thing. So, anyways, it might be voltage or it might be pressure. Does everybody have this written down? Yeah, okay. So, if you graph the position over time, sketch this out real quick. It's going to change, guys. I know this is kind of a review from the last time we met. You might remember this now, but will you remember it in a month? When we take well, it won't be a month. It'll probably be more like 2 weeks when we take the test over this stuff. In 2 months, we're going to take a final exam. So I got to get this in your brain 27 times. The funny thing about seeing it on the board is it goes in your brain one time. When you write it down, it goes into your brain another time. If you look at your notes when you go to do your homework, it goes into your brain another time. The actual homework problem itself puts it in your brain. And if I give you 3 or 4 questions, I get pretty close to that 27 mark, right? Anyways, what does this graph mean? Well, it's the position over time. So this could be a pendulum, right? So I'm going to do some rough sketches. So you could have a pendulum like this. This is your equilibrium position. And it could swing this way. And that would be 10 centimeters. And then, because of physics, it would swing 10 centimeters this way. And so what you're measuring over time, how it swings. Now, that's a pendulum. I heard a guy call it pendulum the other day. I was like, okay, which is probably how it should be pronounced. The other way is a spring, so you could have a horizontal spring. So this is your equilibrium. And then it gets -10. And so we're measuring how that bounces back and forth over time. It could be a vertical spring. Oh, I had to spell the words out. That's way too much work. That's where I screwed up. I want you guys to sketch these out so you have an idea of how it works. So you have 3 positions. This is the equilibrium. Actually, you don't have to sketch this one out. This is the short one. This is the long one. Where this is 10 centimeters, this is -10. And this is the equilibrium. All right, so if you measure that over time, it'll look something like the graph that you see here. Okay? And then this is the type of question where you don't need to make a conversion. If I say, what is the amplitude of this? And it's measured in centimeters. How do I know it's measured in centimeters? It says it. And the same thing, it should be in seconds if you have to do motion or energy. But, how many, what is the period of Earth orbiting the sun? Well, it's a lot of seconds. So you could say 1 year. Okay. Just depends on the question. But if I ask you what is the kinetic energy of the Earth based on the period or something like that, then you got to convert stuff. All right. Did everybody have all this stuff written down? Okay, let's go on to the next one. So the mass attached to the spring oscillates on a frictionless surface. Okay, so that means we're going to ignore friction. I will say this, though. Friction dampens the oscillation. It's a dampening force. Okay? We're going to talk about that today. So at the equilibrium, the restoring force is 0. Right? There's on a horizontal one, there's nothing pulling on the block. The block's just sitting there, and the spring is just at its free length. Okay? It's different if it's vertical. All right? It's different if it's vertical because gravity's pulling down on it. So sometimes we have to, depending on the question, you might have to consider that too. Now, when the mass is displaced, the restoring force points left. Why? Because the spring wants to stay this way. It wants to stay in equilibrium. Okay? So the force of this spring is going to pull it this way. And then it's going to pull it this way, but because it has momentum, because in order to move the block, I had to do work, right? So I did work. Which means I added energy to the system. And energy is conserved, so it went back this way to this position. And it's equal, right? Because the energy is conserved. It wouldn't go further than that. And it's a frictionless surface, so nothing is eating up the energy, in theory, right? So when the mass is displaced, the restoring force, in other words, it's compressing the spring, the restoring force is going to go to the right. Why? Because it wants to stay like this. It wants to stay in a point of equilibrium. The whole universe has a design. It's funny. The entire universe is dynamic in the sense that everything is in motion. Everything is happening all the time. But it always wants to be in a state of equilibrium. The light bulbs work because the electrons just want to stay where they are. When you pump a bunch of electricity through the electrons, they get excited. They enter into a higher energy state. They can't stand that, so they have to release photons, light, for them to go back down, for them to give off the energy they absorb. Everything in the universe is in motion. There's nothing really standing still. You say, well, Mr. Adams, rocks stand still. No, they're made up of elements, and those elements have electrons. And those electrons are cranking around the nucleus of the atoms. It's kind of fascinating when you think about it. But eventually those electrons will run out of energy. It'll be so long from now, you won't even care. Like billions and billions and billions and billions and billions of years. Okay. Are we almost done? Can I go to the next slide? Okay. A vertical spring, the only thing that's different with the vertical spring is that your equilibrium is going to be beyond, it's going to be beyond the free length, right? Because gravity is going to pull it down. But the net force is 0. That's very important. So write this stuff down. I know you have this image drawn a lot, but just write down the difference, because above the equilibrium, the restoring force goes down. It basically goes in the opposite direction. It goes in the direction of the spring wanting to stay in that state of equilibrium, right? Now, when the mass is below the equilibrium, the restoring force is to go up. So it wants to stay in equilibrium. It wants to stay here. So when it's compressed up here, the restoring force pushes it back down because it wants to stay here. And when it's over here, the restoring force pushes up because it wants to stay here. Okay? And whether I push it up or pull it down, I'm adding energy. So in order to get this thing moving, I had to add energy, or I did work. Okay? They talk about this in like biology and earth and space science when they talk about systems, but I want you to think about something. The sun is a nuclear reactor, and part of that nuclear reaction gives off tons of heat, tons of light. That heat warms our climate on Earth to sustain life. The subatomic particles, the photons, the neutrinos, all those things that come from the sun to Earth, in a roundabout way, the plants use that energy to make simple sugars. Animals eat the plants. As human beings, some of us eat meat. Some of us just eat the plants. It doesn't matter. But the energy that we have in our body comes from the sun. And then we use that energy to pull the pendulum down or up. And the nuclear reaction in the sun was set in motion a long, long time ago. Long time ago. So it's just fascinating. But you know, at some point, that nuclear reaction in the sun will eventually end. It's like billions of years from now. But there'll be other stars. Can we move on to the next thing? All right. So now it's the same thing for different oscillators. So for pendulums, it's basically the same thing, right? The restoring force is going to go towards the equilibrium, right? So this is my equilibrium, and this way is kind of the restoring force. And when it's over here, my restoring force is going to go back to the equilibrium. Everything points back to the equilibrium. So energy oscillates between different forms. Pendulum, the energy oscillates from gravitational potential energy and kinetic energy. So just like when we were doing free fall, this is going to be almost all potential energy, right? Over here, because think of when we were doing free fall. We shoot a ball up in the air at its maximum height, what does it do? It doesn't really move. It stops. Okay, for that instant in time, it stops. And when it stops, it's 100% potential energy because gravity is going to pull it down. So at the maximum height on a pendulum, it's all potential energy. Well, when does it have the maximum kinetic energy? Right here at the equilibrium. If I throw a ball up in the air, when does it have its maximum kinetic energy? Right before it hits the ground. The instant before it hits the ground. And just to kind of refresh you guys' memory, what's the formula for kinetic energy? Anybody know that off the top of their head? 1/2 times the mass times the velocity squared. Okay? That's not a very good V. I know somebody's going to write a U down and think that's the potential energy. Like, Mr. Adams, I kept getting the wrong answer. Okay, there you go. So pendulums oscillate between gravitational potential and kinetic energy. A spring, the mass systems, the energy oscillates from elastic potential. I'm just going to say spring, right? Because that's how we learned it before. Spring potential energy, that's what the formula we wrote down before. And kinetic energy. Okay. Is there any questions on that so far? Can I move on to the next slide? No, not yet. All right, that's fine. All right, can I move now? Not yet. Oh, you guys are still writing stuff down? All right. Can I move on now? So it says which, you don't have to write this down, I just want you to think about this. Which position is the block moving the fastest? Probably at the equilibrium, right? Because that's when it has the maximum. So remember, over here, and like I said, you don't have to write this down. This is all potential energy because it's literally stopping right before it reverses direction. But this is the maximum kinetic energy right here as it reaches the equilibrium position because there's zero restoring force. Okay, So it says at which position is it at rest, B and C for that moment in time, right? So if it's mostly potential energy, that means that the velocity equals 0 at that instant in time, and that this has a velocity that's equal to 0 at this instant in time. When does it have the maximum kinetic energy? Here. And then when does it have the most potential energy? We've kind of labeled that as B and C. Does that make sense? Okay, but you don't need to write that down. I just want you to think about that. So as an oscillator passes through the equilibrium, the restoring force is 0. Oh, let's mention that. So right here, I said it, but we didn't write it down. So this is restoring force equals 0. Okay? Why? Well, the spring isn't going to pull it one way or the other. It isn't going to push it. It isn't going to pull it. Okay? At that instant in time, the spring is happy. Remember, it wants to stay in the state of equilibrium. So it has inertia. It keeps moving until a force is applied long enough to change its motion and bring it to a stop. So even though the spring isn't really doing anything on the object because it has inertia, or you can kind of measure inertia with momentum, it's going to keep moving. It has kinetic energy. It has motion. It doesn't just stop. Remember, an object in motion will stay in motion forever until a force acts upon it. Just because there's no force acting upon it doesn't mean it's not going to, it's still going to keep moving. If I was out in outer space and I threw a rock, that rock, because it doesn't interact with any friction, will go on forever until something stops it. Maybe it gets close enough to a planet where the planet's gravitational pull will pull on it. Maybe it'll hit something, but it's going to go forever in a straight line. It's never going to stop forever. Okay? All right. Which of these things will change the effect of the mass on the spring? You don't have to write this down. You just have to think about it. Will the mass change it? And how will it affect it? So the mass affects the period. It takes more time because it's going to affect the amplitude, right? Now, the spring constant, if you increase the spring constant, it'll change the period as well, because it's going to go faster or slower, because the spring will have a greater or lower restoring force. And the amplitude can have an impact on all of it, right? How far it goes may take more or less time. So it really impacts the period. When mass increases, frequency decreases. When the spring constant increases, frequency decreases. And when the amplitude doesn't affect the frequency, though. It's just because the frequency is kind of based on the amplitude. Like it doesn't change it, right? Now this you got to write down. So ideal oscillators continue oscillating forever, but they don't exist. There's nothing in the universe that's ideal or perfect. Real oscillators in the real universe have friction. Now there are things that are close to ideal, like electrons in an atom, but they're not perfect. They can't be. So most oscillators have a dampening effect, and the dampening just decreases the amplitude. That's it. It's called dampening. So, and it's usually due to friction. Friction slows things down. And really what happens is when something comes in contact with something, it doesn't always have to come into contact. It could be gravity. But it converts mechanical energy into heat. Like when you take your hands and you rub them together like this, first thing that happens is your hands get warm. Well, that's energy. Where's that energy coming from? Well, the kinetic energy is getting converted into heat energy. On a molecular level, what's going on is the molecules in my hand are bumping into each other. Because they're bumping into each other, they're absorbing energy. In other words, my hands are in motion. It has kinetic energy. It's causing the molecules in my hand to bump into each other. That extra energy is absorbed by the electrons. They want to be in a state of equilibrium. So in order for them, so they enter a higher energy state, they want to lower their energy state and they can give off heat. That's a simple way to explain it. So they give off heat. And that's what friction does. Now this is called dampening. And if you graph it, this is what really happens. So if we had a real deal pendulum and we swung it, this is what happens. If I had something, a mass on a spring, and I hung it and I pulled it, it would bounce back and forth, but eventually it would go towards a state of equilibrium. So everything in the universe starts off this way, but it all wants to go and reach a state of equilibrium. Okay? And I should probably point that out. Remember that this is equilibrium. So what happens in the real world is everything, and it's usually due to friction. A little friction occurs, and because friction occurs, some of that energy gets used up a little bit more. Every time it goes through a cycle, less and less energy remains in the system. Same thing over here. Less and less energy. It almost always looks like a horn. Less and less energy. And you keep tracking that, it will eventually stop. Okay. Can I move on to the next thing? You don't have to write this down, but dampening is to remove oscillating energy from a spring. Shock absorbers on cars are a good example of this. They're designed to damp out oscillations to produce a smooth ride. You hit a pothole, the tire falls down, right? I mean, if you didn't have the springs, the whole car would fall down. And then when you come out of the pothole, the whole car gets jolted up. Well, these springs have a natural state of equilibrium. Okay? The car is compressing them because the car is heavy. And so what happens when you hit a pothole? It forces the tire down, but the inertia of the car kind of keeps the car level. But then as you come out of the pothole, when it hits the tire, it compresses the spring and doesn't push the whole car up. So if you hit a pothole, it lessens the damage on the car. I think we've written this down a couple times, but basically the amplitude is the distance from center, so you don't need to write this down again. The time it takes to make one full cycle is the period, right? So the period, T, is the time it takes to go from here and back. So capital T is the period, the time. Usually that's in seconds. Okay. When is it at rest? It's at rest here for an instant in time. The velocity is equal to 0. It's at rest here for an instant in time. It's at 0. It has the maximum energy here, so this would be the maximum kinetic energy here. And then when does it have the potential energy? It has the potential energy here and the potential energy here. Okay. So if you follow their diagram of A, B, C, it looks like this. B, A, and C. B, A, and C. Okay. Do you guys want to sketch this out? You don't have to. You probably should, though. Draw that real quick. I probably have written that down 2 or 3 times. If you already have it in your notes, it's fine. But if you don't, you should have it in your notes. All right. Can I move on? So I don't know if you need to write this down. Write it down if you want to. But really, we're just going to think about the forces and how they work. So when it's displaced to the right, the restoring force, a component of the weight, points left. So gravity pulls it down. Remember when we did the inclined planes, we said gravity pulls it straight down, right? So the weight of this object is going to come straight down towards the center of the Earth, and that's going to be mg. And I kind of drew it too big, but I just wanted you to see it. So that's going to be mg. And then we have an x component of it, and we have the y component of it. Okay? And then over here, we have the same thing going on. There's going to be, maybe I'll draw this one a little more accurate. This is going to be, that's just regular mg. And that's just gravity pulling it down towards the center of the Earth. Over here, we have the same thing. It's just straight up mg. Oh, man, when I draw real small, it doesn't like it. Okay? So the x component, this is the restoring force, the x component of this. Now, mg and the tension of the rope, those are conflicting with each other, right? So T minus mg y equals 0. This, you should write this down because it will be helpful for your homework. Okay. So they say, what's the tension in the thing? Well, it's always mgy unless you're at the state of equilibrium, then it's mg. But mg at this point is equal to mgy because it's all going in the y direction, right? At this instant in time. And then the length of the thing. Oh, well, let's finish this and then we'll talk about the other stuff. So those are the restoring forces. So the restoring force really is mgx, is really the restoring force. Okay? When displaced to the right, it points left. When it's displaced to the left, it points right, right? the equilibrium and restoring force shrinks to 0. So there's no restoring force right here. In fact, the only thing that keeps this thing in motion is momentum. And then your restoring force here equals 0. Because there's no x component pulling on the pendulum at that time. All right, can I move on? So you don't have to write this down, but the mass has an impact on the amplitude. The length of the string will actually have an impact. These are all the things that will have an impact on the period, right? If it weighs more, it'll swing more. That means it's going to take more time. If I raise it higher, it'll swing more, which means it'll take more time. If the string is long, it'll swing more, so it'll take more time. Okay? The mass will affect it because if it's heavier, it'll swing faster because the momentum will be greater. Compared to the amplitude, I have to add more work to the system for a greater amplitude. That means it'll have more energy. And then the length of the string has an impact on it too. The period does not depend on the mass. Okay? The period does not depend on the amplitude. The period does depend on the string length. A longer string gives you a longer period. Which is interesting because it kind of does, but what they're saying is if you change the mass, because the restoring force also increases, right? If you increase the amplitude, then the restoring force also increases. If you change the string length, that means gravity is going to have a longer time to have an impact on it. Lastly, we're going to talk about phase, so you got to write this down. You guys might not have a homework assignment. I didn't think it would take this long to do these notes. So a rotating wheel returns to the same place every 360 degrees or 2 pi radians. All right, so we're going back to our rotational stuff, sort of. The idea, this is the idea used to describe phase of an oscillator. 1 full cycle represents 2 radians. So when you look at a graph, and I do want you to sketch this graph out, let me write it down here where there's more room. Oh, I wrote that down wrong. That's actually time. So this is time. and we'll call this position. This is equilibrium, though. So we start here. And we can think of this as the maximum height or whatever. And so that would be the highest point. Now, as I rotate through here, this might be a state of equilibrium. Actually, let's make this the state of equilibrium, because equilibrium tends to be the halfway point, like, right, one full cycle. So think of a pendulum, right? This is my equilibrium. Well, if I start over here, this will have a maximum position, and we'll label that as X. All right, or, well, let's not label it as X. Let's just call it position. So now, remember that when you reach your state of equilibrium, if this is my max position, as I get to the state of equilibrium, it's kind of like the zero, right? I'm going to be above and I'm going to be below. So as I get right here, that's about the halfway point. And then when I get right here, that's my state of equilibrium, which is 0. Then when I get right here, it's the exact opposite. So that would be like here. So I've got 0, and then I've got here. And then again, it oscillates back up. So when I'm here, right here. Right, that one got deleted somehow. And then when I'm here, I would be about halfway up. And now I've started all over. So that's one full cycle. So one full cycle goes from here all the way down to here and all the way back up to here, roughly. Okay? Now, this whole thing from here to here is one cycle. Now, in terms of how does that look on a pendulum, well, this is my maximum, so it's here. When it gets to be about right here, that's this point here. When it gets to be here, it's here. When it gets to be about halfway this way, it's here. And when it gets to the maximum in the negative direction, so we'll just call that negative max or min, that's going to be the lowest value that'll be negative in the negative direction. Then when it gets back here halfway again, that's here. When it gets to equilibrium, that's here. When it gets to this point about halfway, that's here. And then we're back at the maximum, that's here. And as long as that pendulum or spring or however you measure, as long as you keep doing it, it's going to create a wave, right? It's going to go like this. And it just keeps going, and the period is the time that it takes. So the period then would be from here to here, and that's the time for one cycle. That's your period. Okay? You guys have that written down? All right. Can we move on to the next slide? Okay, cool. So here's a little bit of a breakdown if you want, but it's basically the same thing. Okay, and these will be posted online if you need to look it up again. But that's what's going on. Degrees and radians. Now you do need to write this out. It says position. We're gonna have to end the notes here soon, but position. Go ahead and sketch this down real quick. things can be in phase or they can be out of phase. In phase is an interesting dynamic because the maximum amplitudes are synced up. Out of phase, the minimum occurs at the same time of the maximum. So I'll just give you a second to kind of sketch those out. This is actually what happens if you're in band and you're out of phase. So some frequencies, because the cycles, like a higher pitch instrument, will have a higher frequency. But lower frequencies are longer waves, so they can be out of phase. And what happens is over here, this is going to be a dampening effect. So this is dampening, kind of, they cancel out. Dampening is not the right technical term. It's lower. It lowers the amplitude. It cancels out. So this is deconstructive versus constructive. So this will be constructive, which will be louder or more. This is like what I did with the tuning forks, right? It got louder. Well, they were in phase with each other. Okay. This is deconstructive. So being out of phase, and I have a couple band kids in here, and they're looking at me like, what? So I have this. This is 512 hertz, or it's a C note, right? If I take the C note and I pull it up to here, nothing. Because this is tuned to A, which is 880. It's a higher octave, but it doesn't matter. See how I do that? Nothing happens. But now, this is 880 hertz, which is A. This is 880 hertz. This is constructive. Watch. So what's going on is that the bottom tuning fork, this is one tuning fork, and then it causes this one to vibrate, but because they're in phase, it's louder. And deconstructive, it's not louder, it's softer. Okay, I think we'll pause there because class is literally almost over with. And then we'll finish up the rest of this tomorrow, and I'll give you homework.